During the break, I figured out what was wrong. I just had to try again. I don't know what was wrong. All I did was go to Tools. I noted that Port was available as an option, and it was just blank. It didn't have anything by it. So I chose COM13, which is the only one available, which is where the Arduino is apparently connected, and it downloaded just fine. So, like I said, plug in, unplug in time helps. I don't know why. Sometimes that's the way it is. What I wanted to do now is run the program, so let's go back and run the blink sketch. And what we'll do is play with it just a little bit so you can see how it works. When you have a sample bit of code you can run, and then you can modify the code a little bit, you can learn more about the commands and how they work. All right, so if we download this to or upload it to the Arduino, if you notice the TX and RX lights were flashing. You couldn't see it, but you could see it up here while it was downloading. And now the program Blink is running. If you guys want to come up and look at it, please do come up. For the sake of the video, I'm showing the LED blinking. So just on the board. So you see it turning on and off. Pretty simple, dumb program. Okay. Why don't you guys gather around again? I like talking to you here rather than at a distance. You're fine. If you don't want to, you're fine. It's your choice.
I had to deal with Arduino when I did the 3D printer project.
So
everything was all on
you are going to be very bored for the next class or two.
Probably today, yes.
And I don't blame you. That's fine. I was talking to Mr. Wellner during the break, and he said the electronics portion was very slow and boring for him. The only reason I go through it at such a slow pace is because I found that a lot of mechanical students in the past they couldn't do what I was showing you guys. So that's why I went through it. So if it was slow for you, I apologize. And you mentioned something during the break, Mr. Wellner. I've forgotten what it was.
In the code? How come it's color-coded?
Color-coded, thank you, yeah. The reason for that is, well, here, I'll just demonstrate. Let's say you type PIN-MOD for pin mode. Well, the compiler doesn't recognize it. It's as soon as the compiler recognizes the command or the function that you're trying to reference, it changes the color to let you know, hey, I know what that is. Because it's a visual, quick, easy way to avoid mistakes is what it is. Yep. And it has different colors for various things that it recognizes. And notice if I do this, out PU, it doesn't know what that is. I have to put a T on it. But a lowercase t is not good enough. It still doesn't know what that is. I need a shift T. Okay? And then when it changes color, I know that it knows what that is. So it's kind of like a pre-compiler. It's error checking. Okay. What do you think will happen if I do this?
2 seconds.
2 seconds of what?
It'll wait 2 seconds between. Not 2 seconds.
Almost. It's 2 seconds on and 1 second off. You can see the LED flashing. Because that's all I did, right? I made the delay after it turned the LED on. So it's still off for 1 second, but it's on for 2. So, you know, simple stuff you can do. What if I switch these two? What if I make this low and the other one high? Well, it'll just be off for 2 seconds and on for 1, right? Only problem is I haven't used the correct command. It doesn't recognize what I'm talking about. It recognizes that one. If I try to compile it, it says low was not declared. In other words, you got a variable, but I have no idea what that variable is. Okay. Okay, we've beaten this one to death. Let's move on. Something a little bit more interesting. What about the button program? Let's see. Examples, digital button. Remember, this was the simple program that when you press the button, it would turn the lamp on as long as you held down the button and turn it off when you turn it off, when you release the button. So let's run this one. Now, the program is in the Arduino. It's ready to go. But I don't have the button or the LED connected, right? Okay, in fact, LED pin is 13, so that means it's going to use the built-in LED. We'll connect to pin 13 and see if it can drive an external LED as well. Okay, so we'll do that. We'll do it one step at a time. We've got a button here. I'll show it to the Anderson students. You can actually buy arcade quality controls, which I've done. This one's kind of an older style. It's got a Microswitch on it, but the Microswitch is vertically oriented. When you press the button, the mechanical button, the electrical button is pressed down here. It sticks a lot. I hate this type of button. Okay. The other type has the switch oriented the other way so that it's not a wedge, it's a press. I like that type a little bit more. I couldn't get it off the wood though, so I brought this one instead. This microswitch is normally open. In fact, if I doubt you can see this on the video, but I'm going to try, and we'll pass this around as well. There are some markings on the microswitch, and if you took apart a microwave, the door switches are microswitches just like this, and you can take them off and look at the markings. One of the markings says NO, the other one says NC. NO stands for normally open, NC stands for normally closed. A lot of times these microswitches will have a common and a normally open and then a normally closed pin. This is only a 2-pin device, so this is a single pole, single throw. But anyway, it's just a simple switch, and we can use it for putting input into the Arduino. Before we do that, I'm going to put input to the Arduino even more simply. I'm just going to use a piece of wire and connect the input pin to the voltage rail or the ground that's on the Arduino. If you look on your Arduino, you'll see on the silk screen that there are pins labeled VN or V, voltage. How did they label it? VN, 5V, and 3.3V, as well as GND. So we don't want VN. VN is where you would put power into it. We'll connect a wire to the 5-volt pin. So I'm connecting the wire to 5 volts. It's this green wire here. And then I will touch that to the input. Now what was the input pin again? What was the button on? Pin 2, remember? So I'm going to connect that to pin 2. As soon as I do that, as soon as the wire is connected to pin 2, you can see that the LED on the board is actually on. Whenever I disconnect it, the LED turns off. Not really all that exciting, right? Wait a second. I disconnected the pin and it didn't turn off. What happened?
It's latched.
It's floating. That's right. There's enough charge on here. In fact, if I touch, I'm going to do something different. I'm going to take this wire out, put it into pin 2, hopefully very carefully. Nope. It was enough. I didn't even have to touch it. I was going to touch it and drain the charge to my hand, and you'd see the light go off. Just putting the wire in was enough to drain the charge, and the LED now went off. Okay. So really what you have to do is you have to connect. It's floating, by the way, and I can touch it and do various things and get the light to flicker. But you either have to connect to ground, which is the LED off, or you have to connect to 5 volts, and the LED is on. You guys can come up and look at it if you want, or just believe me what I'm saying. So the LED is on. If I pull it out, LED is still on. As soon as I connect to ground, let's see. Well, the charge drained before I connect to the ground, but that makes it off. So you can see the value of a pull-down or a pull-up resistor, right? So let's hook up the, I can get this out, man. Let's hook up this button to some breadboard. And you've probably all dealt with breadboard, but in case you haven't, here's what it looks like. The breadboard itself is this bit here. It has rails, a positive rail and a negative rail on either side. Typically that's what they're used for. They're marked that way. And then each of these holes in the center are connected to each other. Does that make sense? So you can make connections because each of these rows are connected to one another. And typically you put chips along the center. It's spaced for that. Anyway, what I'm going to do is hook up a couple of things. And I'm sorry for the Anderson students, you won't be able to see this. I don't have a free webcam that I can point towards the board, but I'll describe what I'm doing. I'm going to connect the button to one leg in the meat of the board, in the center area, and then the other leg I'm going to connect to positive voltage. Now that'll go through several connections because I'm going to tie this rail on the breadboard to the post that is for positive voltage VA. Should be a hole in it where I can stick this through. And the guys here in New Albany will probably want to come up and see what I'm doing. Any of you have a cell phone or something you can take a picture of this once it's set up for me? Not right now, but if we can do that a little bit later, I'd appreciate it. And then I'll add that in for the Anderson students. If I can get fancy and edit the videos, I'll bring it up while I'm talking about it. So then, let's see, I need another wire to jump over to the actual 5-volt source, which is on the Arduino. Where do you think the Arduino is getting its 5 volts from? It doesn't have a battery in it. What do you think? From the USB, exactly. So we don't have a whole lot of current available here because we're limited by whatever the USB can do. But that's where it's coming from. Okay, so I've got the 5 volts connected. Now let's connect ground. How many of you guys have played with Arduinos before? 1, 2.5. Okay. So really this is the negative side of the supply, but ground's good enough for what we're doing here. And I'll try to use color-coded wires so this makes some sense. So all I'm doing is applying wires to the power side of the breadboard. One thing to note about breadboard is that the power rails have a break right in the center. If you forget that, you think you're applying power to your circuit and you're not. So I'm going to jump those power rails just so that I know I've got power on each side. So usually you just use a very small jumper across the center. And you guys may want to come up here and look at this so you understand what I'm talking about.
Shoot the table.
Yeah. No,
So all I've done is I've put a jumper wire across the 2 halves of the power rail for the positive side and for the negative side because they're not connected internally. So that's why you need these. And you'll see those on breadboard all the time. You wonder why do people leave some wires on the board? Well, because 9 times out of 10 you're going to want them. Also, the power rails on either side are not connected to each other. So a lot of times you'll see jumpers going across there as well. Okay, so something worth knowing. So right now, I actually do have my button connected where I can jump 5 volts to this line on the breadboard. Okay, to a line on the breadboard for the sake of the Anderson students. Turn this so we can see it. So now I can put 5 volts there by pressing the button. Well, what do I want that 5 volts to do? I want that 5 volts to drive an input pin. Okay, I can do that. And the input pin was pin 2. Well, this wire is not long enough. Let's try a longer one. That one's longer. Have I finished the circuit? I can press the button and the light goes on. When I release the button, it doesn't go off. What did I miss? Remember, this is a single pole, single throw switch. So what do I need?
something to take a charge off of the input.
Which we called a pull-down resistor, right? I need a pull-down resistor. Do I care? Not really. Here's a resistor. I'll hold it up for the Columbus students to see. You probably have plenty in your lab. Hopefully you can see the colors on it. I'll tell you what they are. They are brown, black, orange, and gold. I read them in that order because the gold line is the tolerance, and I know that. Okay. A lot of times there's a little bit of extra space between the tolerance bands and the bands that represent the number. What does that mean? What's the value of this resistor? Do you guys remember? I'll tell you how I remember it. You can either go and look up a chart, or you can remember the colors of the rainbow. Okay, colors of the rainbow: red, orange, yellow, green, blue, violet, right? And the only key is to remember that red is 2. Okay? So if red is 2, orange is 3. I guess I should hold up the right number of fingers, shouldn't I? Orange is 3. Right? Red, orange, yellow's 4, green is 5, and so on. Okay? Until you get to 9. Most of the time, that's all you really need. Going past green, get into yellow. Yeah, there are resistors out there like that, but resistors don't have to be a very certain value most of the time, and this is another one of those cases. Anyway, the first 2 color bands represent numbers. So brown, the other thing to remember is that black is 0, okay, and brown is 1. So if you remember that, then red is 2, and so on. Okay. So our rainbow needs to be black, brown, red, orange, yellow, green, blue, violet, okay, for the color codes on the resistor. So if we start with brown, what is that again? 1. So we got 1. Then we got black, which is 0. So far we've got 1, 0. The third band is not another number, it's the number of zeros. Does that make sense? So the orange stripe, orange represented what count? 3. So it's 3 zeros.
So it's 10K.
10K, exactly. It's 1 0 with 3 zeros is 10,000 ohms. And that's what I suggested we use so that we're drawing a half a milliamp every time that the button's pressed. Okay. So all I've got to do is connect this. I'm going to move my button connector over just a little bit. All I have to do is connect this resistor to ground to be a pull-down resistor. Now when I do it, the light's off, press the button, light goes on. As soon as I release the button, the light goes off. If you guys want to see it, you can press the button if you want to. I need to clean it, make it operate better. Now what would happen if I hooked it up the other way, where the button is supplying ground and the resistor is supplying positive voltage? What would happen in that case? Turn it off when you push the button. It would be the inverse logic. Now there's terminology for this. Right now the button is connected to positive 5 volts, so it is considered sourcing current. Whereas the resistor is connected to ground, so it is sinking current. Okay? So we're going to make the resistor source, and we're going to make the button sink. If I can get the wires into the holes. There we go. Now the LED is on if you look at it, because the resistor is always connected to positive, okay, and then it's connected to the input. You can see it here. If you come look, you're welcome to. Press the button, it goes off, exactly as we expected. Okay. Now the other part I said I was going to attempt is to hook up an external light emitting diode. Okay. Now to do that, I'm going to need an LED, so excuse me for a moment while I grab one. And I've got one over here somewhere. I forgot to look for one this morning. The jump table. Let's see, here's one. Sorry, it's probably good. Got an LED, and we'll need a resistor. Now, I may have to scrounge for a resistor. I've got some in here, but I don't know if I'll have the right value. So I found a light emitting diode. This is an encapsulated LED. It's just a red diode. The encapsulation's red too to enhance the color, I guess. If I hook this up right now, what will happen? I'll have to go find another LED, right? That's what will happen. So I need a current limiting resistor. Let's see what we've got in here. Let's see, we've got a red, red, yellow. Would that be a fairly high resistance or fairly low? It would be fairly high because that yellow indicates 4 zeros, right? So it's on the order of 100,000 ohms. Yeah, yeah, 220K. Good job. That's it. That's too much, right? This LED is not going to turn on when we're putting less than a milliamp through it, so that won't work. A 10K is too large. What is this one? This one is a brown, black, brown. What's that? 1 0 with a single 0. So it's 100 ohm. That's a little closer to what we want. Let's hang on to that one. If I put 100 ohm to 5 volts, right, in series with this LED, what's the maximum amount of current that could go through the LED? 5 volts over 100 ohms, right? So 5 over 100. Wouldn't it be 50 milliamps? You just move the decimal place over twice. All right, so 50 milliamps. That would probably burn out this LED. This is a really cheap LED. It's big, but it's probably cheap. Let's see what else we've got in here. Here's one. This is a brown, red, brown. That's a little better. This is 120. So 5 over 120 is how much?
42.
So 42 milliamps. Probably still wouldn't have an LED very long. Here's a brown, gray, brown. That's where I have to go look it up, because I don't remember where that falls. But that's even better. It's going to be a higher resistance. Let's see. That's about it. What I could do, I could use a couple of these resistors in series. When you have resistors in series, how do you calculate the effective resistance? Just add them, right? If they're in series, you just add them. So we could put 100 with 120. We'd have 220 ohms of resistance. So 5 over 220, I think we already did that math, didn't we? In the example, because I had that. As an example, I said how much current would be flowing.
Was it 23?
Yeah, I think it was about 23, 24 milliamps. That's reasonable. That's something I don't think will blow out this LED. So that's what we'll do. All right, so let's see. Just to run the LED from the very beginning, what I'll do is connect a resistor from 5 volts on the breadboard. I'll do it on the other side away from the switch so that you guys in Anderson can see what I've changed, because the original circuitry is on the right-hand side with the button, and the new circuitry for the LED will be on the left-hand side. So I'm putting 2 resistors in series on the breadboard. And I apologize that I don't have a camera so you can see me actually do it. I'm going to hook the black lead, which I hope these students knew what they were doing. I'm going to hook the black lead to ground, and I'm going to hook the red lead to one side of the resistor. Hey, it came on good. They did know what they were doing. So the LED is on. All I'm doing is running power through it. And this LED is not super bright at this current, so it probably could take this indefinitely. If it was really bright, I'd pull it out quickly and try to save the LED. So we've got about, a little over 20 milliamps, and that's still approximate because these resistors have a decent tolerance zone. The gold color on them is plus minus 10%, if I remember right, and silver I think is 5%. Okay, so it's about 220 ohms. This is about 24 milliamps. If we had a multimeter, which we do, if I really felt like going and getting it, we could go measure how much the voltage drop is across the LED and what the current is. Right now, I don't really care about that. So I'm not trying to just make the LED turn on and leave it on. I want the Arduino to control whether or not the light is on. So what do I need to do? Well, I need to allow the Arduino to be either sourcing or syncing, right? So how would I do that? Well, the way I would do it is I would leave the negative side of the LED connected, okay, and let the Arduino be sourcing, because the Arduino is going to go between 0 and 5 volts, okay. The other option would be to leave the positive side connected and let the Arduino be syncing. So when the Arduino's output pin goes high, the LED would be off. It's the same thing as what we were doing with the switch, the button, whether it was syncing or sourcing. Okay, but it usually makes more sense to students if you let the control device be sourcing instead of syncing. So the LED pin was pin 13. If I just go and connect this red wire from the positive side of the LED to pin 13, what do you think will happen to this LED? It'll blow it up again. I also may damage the output on the Arduino, because the Arduino's output pins can only source so much current and sink so much current too. So what I have to do is be more careful. I'm going to lift the ground. In other words, I've disconnected the LED again. I'm going to connect the ground to the resistor, and I'm going to connect the end of the resistor, instead of to positive, I'm going to connect it to negative. So now basically what I've done is I've put the resistors underneath the LED to ground. And now I can connect the positive pin of the LED to the output pin on the Arduino for sourcing. So let's see, 8, 9, 10, 11, 12, 13. There we go. Sure enough, the LED is on. Okay. Now remember, I switched over the button so that the button is syncing instead of sourcing. We expect that when we press the button, the light will go off. Sure enough, that's what happens. Okay, there we go. But that's a pretty boring program. Let me change the button back. You know what, actually, yeah, let me change the button back to where it is syncing. I'm sorry, where the button is sourcing and the LED is syncing. The resistor is syncing. I'm sorry, I'm messing up here. So the resistor is syncing and the button is connected to positive, so it's sourcing. So now when I press the button, the LED comes on just as expected. Okay, so this is the button program the way it's intended. Yes, sir?
For the resistor going to the ground, is
Yeah.
that what keeps the breadboard from being damaged, or the Arduino from being damaged?
The resistor with the button,
No, the one you just moved.
the one I just moved is the one with the button. So all I did was I changed it from a pull up to a back to a pull down resistor. That's all I did. These two resistors over here, this 120 plus 100 ohm resistor that is in line with the LED, that prevents the LED from blowing up and the output from dying as well. Okay, so basically on the left hand side of this board are the two resistors that are serving as current limiting resistors. On the right hand side of the board with the button is a resistor serving as a pull down resistor. Okay, they've got different purposes. Okay, so far this is very boring. Now let's do some coding. I wanted to make this so that basically the Arduino remembers the state of the light, and all the button does is toggle the state of the light. Okay, so that's what I'm going to do next. All right, do I need to change much of anything? Really all I need to do is change the logic, right? Because look, I can still use button pin 2, LED pin 13, the electronics are hooked up. Button state is something I will still need to know, so I'll still use that as a variable. And the modes of the pins are still the same. All I need to do is change the logic in the loop. Now I will need to read the button state. Now understand that since this loop is running over and over, the state of the button is being read constantly. This is called polling. Okay? It's in contrast to using something called interrupt driven. Okay? Interrupt driven is where you connect the pin to an interrupt, and when the button is pressed, other circuitry in the Arduino says, hey, the state of this has changed. Hey Arduino, you need to take care of this. And you call a separate function called an interrupt function that takes care of whatever the button needs when it's pressed. Okay, polling is not the best idea because polling like this takes time. The amount of time required to go through the entire loop is increased because we're reading that button every time. It'd be nice to let some other circuitry take care of that and monitor it, be sort of a watchdog for us to indicate and say, hey, something's happened, we need to go take care of it. But I'll show you how to do that later. We'll leave it as polling right now. So button state equals digital read button pin. Now the problem is we need to remember what the button state was, right? So that when the button goes, or what the LED state was, so that when the button's pressed, we change the state if the button has changed state itself. Does that make sense? This could get a little bit complicated. So we don't just care about button state anymore. What we care about is what the button state is now and did it change. Okay? All right, so we will have to remember something. We will have to remember the previous button state. There's a couple different ways to do this, or to tackle this problem, but this is the way I'll do it. So let's say prev button state, okay? Or better yet, since we started off the variable with a lowercase letter, I will put previous here at the end, okay? And I'll say equals button state. Try to put a period at the end of the sentence instead of a semicolon. That doesn't work. What is this doing? Well, I'm going to need a new variable called button state, prev, for previous, and I'll declare that up here. But it's going to store what button state was before we read it. Does that make sense? All right. So before I forget to do it, I'll say int button state prev equal 0. And I'll put some comments here. Okay, so let's see, variable to remember previous push button status. Okay? Now I'm going to save this as something else. I don't want to overwrite the example in the IDE, so I'll say file save as, and I'll just call this toggle button. Okay? We're not done yet. so far the code would run exactly as it did before. We're just having to do it a little bit more. I have to change the logic itself. So the condition is not if button state is high. The condition is if button state was low and went high, then what we have to do is change the status of the LED. Okay? All right, so there's a couple different ways of doing that as well, but let's see. I always have to remember how to do this. I think it's double ampersand. It's a logical AND. Do you guys remember what an AND is? If 1 and 1. What is 1 ANDed with 1? Do you remember that from controls? 1. What is 1 ANDed with 0?
0.
Right. Okay. So if button state is high and button state previous was or is low, what does that mean? That means this button has just been pressed, right? A minute ago, or just a second ago, or probably literally a nanosecond ago, the button was off and now it's on. Since the button has changed state, then what we need to do is toggle LED status. Okay. What about the else? Do we need an else at all? No. If it is not true that the button has been depressed, we don't do anything. We just leave it alone, right? So let's get rid of the entire else section. Notice I've gone from open curly bracket to closed. I'm getting rid of the else statement. Well, what about this curly bracket? Well, if you go next to it, you'll notice that the IDE nicely highlights the matching curly bracket, which is really convenient because you can get confused pretty quickly about which bracket goes with which. Okay. Another good practice is to line up that bracket with the command that it begins, okay, or that began it. Okay, so that's why these are lined up. So I got to figure out how to toggle the LED status. There are some clever ways to do it. One way to do it that's not so clever is to use a variable to remember whenever the whatever the status of the LED is. I'm going to see if I can figure out a better way to do it though. I'm going to cheat just a little bit and use a digital read of the LED pin. Wait a second. If I do a digital read of the LED pin, I thought LED pin was an output. It is, but you can read it as an input. So I can go and figure out what it is right now. And I can say digital write the opposite of it. Well, basically, if I issue this command, digital read LED pin, it is going to return the status of the LED pin, which is either a 0 or 1. So instead of setting LED pin high or low, I can set it to whatever I read, but I'm going to invert it. I think this will work, but I'm not sure. Okay, we'll find out here in a minute. If I remember right, the exclamation mark means the inverse of. So I think what I'll be doing here is digital reading LED pin. I'll get back a 0 or 1, which I will invert and write out to LED pin. Does that make sense? So just like in math, the stuff inside the parentheses has to happen first. So this will be done first. The pin will be, its status will be gained from the correct pin. It'll be inverted and then written out to LED pin. I think. Let's find out. If it complains, then I've got a syntax problem. And I can't do it the way I'm thinking I can do it.
You would have to do.
Well, it liked it so far. We'll see. What were you going to suggest?
Well, if it says you have a syntax problem, you might have to create a variable that equals digital read.
That's what I was trying to avoid.
Yeah.
Right. So use an intermediate variable. Let digital read write that variable and take the inverse of that variable.
Mm-hmm.
Here I'm just doing it all at once. So let's see if that works. In fact, it's downloaded. Went on. Staying on. I've got a problem. What's my problem? It's not actually staying on. Sometimes it does turn off. Sometimes it doesn't turn on. What's going on?
Button.
Switch bounce.
Switch bounce.
Exactly. So I need to debounce this button, either in software or in hardware. Okay. But the code is doing what I said it should do. And happily, I'm able to demonstrate the problems with a bouncing switch. It worked out. Make sense? Any questions?
Do you get switch bounce in PLC HMIs?
No, because the human-machine interface is typically, well, I mean, it depends. If the HMI has some mechanical buttons, it's the mechanical button that causes the bouncing. If it's a touch screen, you're not going to get bounce because it's an electronic circuit turning on or off. So there's no need for debouncing electrical signals like that. Does that answer your question?
I think so.
Now, if the manufacturer didn't do a very good job with the touch screen, it's still a mechanical touch, and it could be multiple touches. So they have to have a decent touch screen, they need to properly debounce the touch signal itself. Because now your finger is the mechanical contact, and there will be make and break there as well. But that should be built into the HMI if it's even halfway decent. Good question. Anything else? Mr. Plas, you had mentioned something. You said that various versions of the IDE and the libraries can cause various problems. In fact, one of the things he mentioned is that he has some older Unos, or Uno or whatever it was.
Pro Micros.
Okay. And basically, those were old enough, they couldn't work with LED underscore built-in. There are times you'll encounter problems like that, where it should work, but it doesn't because of a version conflict, okay? And like he was saying, sometimes people remove things from libraries and you prefer an older version of a library. A library, by the way, I haven't defined that, but a library is just some code you can use for solving a particular problem. So somebody's already written the program to take care of talking to an LCD screen where you've got character output. You don't really want to deal with all those details, so you import a library that goes with that display, and you use it to call functions inside of it to write out characters to the display itself. Does that make sense? In fact, Professor Cooley needed some help with a force sensing. He just needed a small scale that could sense force. So we got a small Arduino. We got a little LCD display where you could display characters, wired it all up, got a strain gauge on a piece of metal that he could use as a scale, hooked it all up, and wrote code and calibrated it so that as you applied force to the strain gauge beam, essentially, the correct amount of force would be displayed on the view. So it was a simple program. But it was just a small program for something he needed in his class. And that's really where Arduino shines, is at making little bitty circuits and programs for doing small tasks. So where microcontrollers shine. But we can make it fairly complicated, and we will in this class. We'll go all the way through PID control using and even velocity profiles using the Arduino. Okay. All right, let's finish off the presentation. We've accomplished that challenge. Let's talk just a little bit more about voltage dividers. And this is something you guys may want to listen in on because there's a little bit more detail here than just a simple voltage divider. You've seen voltage dividers like this before, I assume, where you have R1, R2 as on the left. You can calculate the voltage out, which is between the two resistors, based on the voltage in and the value of the two resistors. And you just use Ohm's law and the fact that the current through the two resistances are equal. Now there's a big assumption built into this equation. Does anybody remember what that assumption is? The assumption is that V out is hooked to something that is very high impedance, so you can neglect any resistor connection essentially from V out to ground or from V out to Vn. Okay? That's a big assumption in this equation. But for the Arduino, where you've got, say V out here is connected to an input pin on the Arduino, that's a good assumption. The input pin on the Arduinos all have very high impedance or high resistance. Okay, so it's good enough for what we're doing. And you see this circuit, you study it in your electronics course, and you think, boy, how boring, who cares? Why not just use a single resistor? Why do I even need V out? Or if I need V out to be different than Vn, why don't I just make the power supply V out directly? Well, the reason is because you don't really need this voltage divider in most circuits. What you're really using is something more like on the right-hand side, where one of the resistors is replaced by a component whose effective resistance can vary. Does anyone know what those symbols are on the right-hand side? That's circular with arrows pointing to it. What is that thing? Anybody know? Almost, yes. It's sort of a light-dependent resistor. Technically, it's a light-dependent transistor. So the base of the transistor, instead of having an electrical connection, the arrows indicate light or photons shining and landing on that transistor in a range that it's sensitive to. Okay? And those photons can actually make the transistor turn on or turn off. For our purposes in this class, we can think of that transistor as a switch. It's either on or it's off. Now in reality it'll have some resistance, but we can think of it as essentially an open circuit or a closed circuit. Okay? What's going to happen to V out if that transistor is basically not there? V out is going to approach what? So there are two of them here. There's one with the transistor connected to VCC. There's one with the transistor connected to ground, and you're correct. You answered for the one on the extreme right. You said that if the phototransistor on the extreme right, which connects to VCC, is not present, then V out will essentially be ground. Okay? Go over to the left just one, and if that phototransistor, the one that's connected to ground, is not there, then V out will essentially be VCC. If either of those transistors close, they will pull V out to whatever they're connected to. So the one on the extreme right, if the transistor is essentially closed, in other words, light is shining on the base, what will happen is V out will go to VCC. Okay? Similarly, for the transistor on the left, if it's closed, V out will go to ground. So you could say that RL on the right-hand side is serving as what? Extreme right, RL connected to ground is serving as what? Pull-down resistor, exactly. The one to the left, the RL is serving as a pull-up resistor. So this is just like the mechanical switches we had a minute ago, but instead of having a mechanical switch, we've got a couple of phototransistors. The reason I showed you this, remember the inkjet pulley, where did I get that? I got to teach machine elements in a little while. Maybe my brain's already trying to jump there. The inkjet printer we took apart. Remember how I showed you the linear encoder for the carriage? Okay, that linear encoder has sensors wrapped around it, and those sensors are phototransistors. And we will hook them up in this fashion so that as a light or as a line comes between the lamp and the phototransistor will be off, and we'll be able to detect that it's off. Okay, so that's where this is going to be really useful for us. Okay. Other than that, I think that's all of my presentation. Nope. We'll do this next time. I've talked too much. Next time I'm going to hook up an op-amp and use it as an audio amplifier and show you how it works. And we're going to let the Arduino play the Mario Brothers theme song for us. That'll give me the chance to show you an array. You guys know what I'm talking about with the Mario Brothers theme song? Okay. We're not too far away from that yet. So we'll do that next time. Questions, comments? Anything else? All right. Well, I'm going to stop the recording. And what I'd like, before I do though, I'd like for you guys to start working on the next challenge already. Okay, it's Lab 2, and it's a program, it's a game. Basically, you have to hook up, I think I specified 8 LEDs. We've got plenty of LEDs over there, plenty of resistors. We don't, ECT has plenty of resistors that we can use. We'll hook them all up to the Arduino, to an Arduino, and I want you to make it where it plays a game. So you'll have a button, and here, I'll just go ahead and read it. Where's the laboratory exercise? Let's go over here. The next laboratory. Use 8 LEDs. I said on the professional development board I need to change that. You'll have to wire them up. So I'll change the statement. But you'll still need 8 LEDs connect to the Arduino. Use a push button. So you'll have to figure out how to do that with either pull up or pull down. Okay. Use a button to, well, you'll have to have 2 actually, because you'll have to have one for starting the game and one for playing the game. And what you'll do is you'll flash those LEDs in any pattern you like, and the idea is that you also need to make sound. And you'll see how to do that later once I show you the Mario Brothers theme song playing. And you do this before gameplay in order to attract attention. Okay, so you're trying to get the user's attention. So you make some sound, you get the LEDs to flash. Hopefully the person comes over and wants to play the game. So the user inserts a coin. That'll be simulated by the start button. Okay, so this button will be as if the user is inserting a coin to play the game. The program will select one of the 8 LEDs at random. Now, why haven't I taught you the random command? And I'm requiring that you use it because I want you to go out to Arduino's website, look for a command that will generate a random number, and figure out how to use it. I can't teach you all of the Arduino coding in the time we have. I don't remember it all. It wouldn't be any better than me going there and looking for the command because I know what I'm looking for and remembering quickly how to use the command. I want you to learn to do that. Okay? So there are commands for doing all this. And I will help you if you can't figure it out. So it'll flash that random LED for 3 seconds. And then what the program needs to do is flash LEDs at random 1 second apiece. So it's just choosing a random LED and turning it on for 1 second. What the user has to do is the user has to remember what the original LED was and press the button when that LED is lit to win the game. Does that make sense? Okay. So you're trying, it's kind of like whack-a-mole, except there's a certain mole you need to whack. Okay. That's all it really is. Now, the user gets 3 chances. If they do not succeed in those 3 chances, there are 3 trials, then there's some sad sound played and the game's over. If the user succeeds, then what you need to do, let me make sure I've got this right. Yeah, if the user succeeds and hits the button when the correct LED is lit, then there needs to be a victory sound and sort of a neat pattern on the LEDs for winning the game. Okay, and then the game starts over. Make sense? So that's your challenge. So we'll devote the rest of the class time to working on that challenge or to writing about the difference between the inkjet printer and the microwave. You can do either one you want. I haven't set a firm due date on Laboratory 2 yet because I don't know how quickly you guys will code. Okay, I do. Do you want this to be a team approach or individual? What do you guys want? Why don't we do teams? We'll do teams of 2. However you want to self-select your teams, I don't care. You guys can work together and figure this out. So, because it is a decent challenge, and I don't want it to take, 3, 4, 5 class periods. It should only take a couple, if that. And I will help you if you have questions. Okay. Probably what I'm going to do is go up to my office and grab my other camera so that if there's questions, I can record your question and our solution to post as well. Anything else? Well, we've only got 30 minutes left in the class. Please, when I release you for... No, we don't have 30 minutes. The class is over. Rats. I'm sorry, I talked the whole time. Next time you come into class, we'll just start with the simple game challenge. Okay, we'll start with that. What I usually like to do, I like to talk for a little bit of time in the class, whether it's maybe 5 minutes to clarify what we're doing, and then let you work on it. During the time that you're free to work on the lab, please don't just leave. Okay, if you have an emergency or something, I understand, but please use the class time to your advantage. I'll be here to help you, and I want you to succeed in all of this. And to me, the best way to learn how to do this is just say, go do it, throw you into it, and I'll help you. Hopefully you guys have got enough background that this is not overly challenging. Hopefully it's not too much. How do you feel about this? Overly challenged? You think it's going to be easy? A tad bit concerned? Okay. Well, that's good. That's about where I want you to be. Anybody feel like this is going to be pretty easy? I know Willie probably thinks it's going to be easy. He's done so much with it. Flash, you're probably feeling like it's not too bad, right? He doesn't know I'm talking to him.
Sorry.
That's all right. I understand. How do you feel about this challenge? Too much, too little, about right?
Second class right out of the gate. It's a little heavy.
A little heavy? Yeah. That's typical for this class because I try to throw you into it as quickly as I can because this is not the focus of the class. But I will be there to help you. Okay. I don't really expect you to have to do a lot on this outside of class time. I think that in class you can get it.